Okay, so thanks to the organizers for the invitation to attend this conference. So the organizers told us that we shouldn't give talks on our own works in this session, but have a discussion. And so the three of us, me, Tirtha and Debtosh, will conduct this discussion about dark matter in cosmology. So let me first start with a one slide overview of dark matter in cosmology, and then we will go into what we shall discuss today. So we all probably know, and I'll keep it at a non-technical level since the audience is very broad. So we all know that the standard cosmological model, the lambda CDM, it fits the CMB anisotropy and LSS data well. And it does not require any non-gravitational interaction of dark matter. And the idealization that we have of collisionless dark matter, it works well at large scales. There is, of course, some room for optional dark matter interactions with itself and with photons, baryons, and neutrinos. And there are constraints on them that have been derived using the CMB and LSS data by many groups. Often one finds that the power spectrum, which is the Fourier transform of the density-density correlation function in the sky, it gets usually suppressed at small scales due to these elastic scatterings, and Tirtha will discuss this in some context. Just to give an example of the kind of bounds that one obtains from these CMB constraints, the velocity-independent dark matter photon scattering rate, it should be around less than around 6 orders of magnitude below the Thomson scattering rate. The key thing that enters through the Poisson equation is the total matter density in the gravitational potential, and it is constrained well. And the baryonic mass density is also constrained both by the CMB and BBN, and those numbers agree well among themselves. And using these two, we can get an idea about the total dark matter mass density. So that's what cosmology gives us. The important thing is low velocity dispersion for these dark matter particles. In particular, if they are non-interacting, the free streaming length should not be larger than around 100 kiloparsec or so. If they're interacting, that will be translated to the Jeans length. And therefore, the phase-space distribution function of dark matter is the key quantity of interest. And I must emphasize that the dark matter particle mass does not enter the collisionless perturbation equations directly. And therefore, the CDM cosmology, it does not constrain it in a model independent way. Of course, the mass and couplings can enter through the production mechanisms in the early universe. They can also enter the perturbation equations in presence of interactions. With that broad overview in mind, we shall discuss today three topics. I shall talk about the very early epochs and some production mechanisms of dark matter in the early universe. Then Debtosh will talk about the kind of Middle Ages. He will discuss the impact of non-standard cosmologies. That is, if you modify the standard cosmology in the pre-nucleosynthesis era, then how that has an impact on structure formation. And then Tirtha will discuss the late epochs. In particular, he will talk about non-standard dark matter properties, so not cold collisionless dark matter. For example, what happens if dark matter has self-interactions, and he will discuss those in the context of structure formation. So let me say at the outright that it is very difficult to make any concrete statements about the production of dark matter in the early universe, primarily because the history of the early universe at photon temperatures larger than a mega electron volt is unknown to us. So this is the temperature, photon temperature line that most of us are familiar with. So we are here, this is the CMB temperature today, 2.7 Kelvin, around 10 power minus 4 electron volts. The CMB photons were generated at around a temperature of 0.26 electron volts, where neutral hydrogen formed and the photons became free. And that is already in a matter-dominated era. Okay. The matter radiation equality temperature is around an electron volt. We know that from the present densities. So before an electron volt is a radiation dominated universe. And from our computations of nucleosynthesis in the early universe, we know that the early universe must have a temperature of at least a mega electron volt. Okay, so that the nucleosynthesis computations are successful. But beyond a mega electron volt, we do not know the history of the universe. In particular, if an epoch of inflation preceded the radiation dominated epoch, which is well motivated as Tanmay just discussed, then the Hubble scale during inflation is unknown, and the reheat temperature, which is the temperature, highest temperature so to say of the radiation dominated era, that also is an unknown. The only thing that we know is that at the end of the slow roll phase, the inflaton energy density has to be less than around 10 to the 16 GeV to the fourth. This comes from the non-observation of tensor perturbation so far. Okay. And of course, we also know that the reheat temperature has to be larger than a mega electron volt because of reasons I just discussed. So given this very broad range of possible temperatures in the early universe, in particular this is 19 orders of magnitude, saying anything specific of what happened here is difficult, and therefore we have a very broad range of possibilities open with varying degrees of testability. The most minimal scenario, of course, is a new field which interacts only gravitationally. Okay, so this is a one-page summary of zeroth order particle dark matter cosmology. You start with the initial distribution function in phase space of dark matter, which might be populated by some mechanism. And then given the distribution function, one needs to answer this question whether it undergoes any significant scatterings. If it does not, then the next question is whether there is any significant free streaming. If not, we end up with this collisionless cold dark matter paradigm, the standard paradigm. If there is free streaming, depending upon the magnitude of the free streaming, we might end up with a warm or a hot dark matter. The hot is not allowed because structure formation, as we know, is bottom up and not top down. And Tirtha will discuss about warm dark matter. If there are scatterings and scatterings with the standard model bath, then those scatterings might thermalize the dark matter sector with the standard model, giving a temperature of the dark matter same as the standard model. This is the simplest scenario, the most studied scenario, and the scenario that can be tested thoroughly. Okay. The other case is that it doesn't scatter with the standard model but scatters with itself, and then it also might thermalize. This is the next simplest one because then we have an additional unknown, which is the dark matter temperature itself. If there are no scatterings or no thermalizations, then the density is related to the initial conditions, which might be the conditions of inflation. Now, I must mention that even with collisionless CDM, although at large scales the prediction would be the same, but depending on whether dark matter behaves in a wave-like fashion or a particle-like fashion, there will be important differences in small scale structure, which again Tirtha will discuss. So let me then talk about dark matter production in the inflationary epoch. There are three minimal ways to do it. One is so-called inflaton decay during the reheating phase, which basically refers to this damped oscillation of the inflaton field around the minimum of the potential after the end of the slow roll, which can be, it's equivalent to a field theory of massive spin zero particles with negligible velocity. And this, of course, requires an inflaton dark matter coupling. The second mechanism is the particle production in a time-dependent background spacetime. Now, the expanding universe is a time-dependent spacetime, and this is a purely gravitational production mechanism, and therefore it is always present. Okay? It does not require any additional non-gravitational coupling to the inflaton or to the standard model particles. So this is an irreducible contribution to the density of any particle. The last one is scattering of a couple of inflaton to dark matter pairs. This might require either a quartic inflaton dark matter coupling or maybe mediated by graviton exchange. So let me start with the simplest one, which is dark matter from inflaton decay in reheating, and emphasize 2 points. That even in this simple mechanism, there are important effects that depend on the details of the reheating epoch. Usually, for these computations, one simply takes the dark matter momentum distribution to be a delta function in the beginning. So the momentum is just the inflaton mass divided by 2 at the end of reheating. However, this is not the case because, as we shall see in the very next slide, there are important back reaction and quantum statistics effects that come into play, along with the duration of the reheating phase, which is an important input. And the second point that I want to highlight is that after getting the initial distribution function at the end of reheating, simply redshifting of the momenta to obtain the distribution function at later epochs is also not a good approximation. There will be inflaton mediated scattering effects that can alter the momentum distribution and therefore alter structure formation constraints significantly. And these scatterings are always present in this scenario because the same reheating process populates both the standard model and the dark matter sectors. And these processes, I want to emphasize, are not subdominant even if the inflaton is heavy, because the S-channel propagator of the inflaton, it scans a broad range of invariant mass simply because we are in a thermal bath. So to illustrate the first point, consider a fermionic dark matter, psi, that couples to this inflaton, and the inflaton also reheats the standard model through this Higgs sector coupling. And in this case, to obtain the distribution function at the reheating epoch, you have to solve this kinetic equation with this collision integral. And here are these quantum effects, this Pauli blocking and Bose enhancement effects that are important. And you see that if you make this instantaneous decay approximation, then of course you obtain a delta function distribution. But the moment you take into account the fact that there is a finite duration of the reheating era, the distribution is no longer a delta function, it is this red solid line. What happens simply is that the quanta that are produced earlier during the reheating get redshifted more. However, the production is maximum towards the end of the reheating, giving rise to this shape. Now, as the dark matter quanta are building up, back reaction effects will start to become important. They will repopulate to inflaton quanta, and once you include the back reaction, you obtain this orange curve. And finally, since these are fermionic dark matters, Pauli blocking effects come into play, and they reduce the distribution further, and you obtain the blue curve. So you see already at the basic distribution level at the reheating epoch, there are important effects to consider, and there are important parameters of the reheating era that influence the distribution function significantly. The second point that I mentioned is that the evolution of the distribution function. So you start with a distribution function at reheating, and the usual evolution is simply by redshifting each momentum bin. So if you want to know the distribution at a later epoch, at a lower temperature, you just redshift each momentum bin. But as I emphasized, that is not an accurate thing to do, because there will be inflaton mediated scattering processes which are necessarily present in such scenarios. And to know the momentum distribution, you need to solve this integral differential kinetic equation with these 2-to-2 scattering processes included. Now, once you do that, you obtain this red distribution function. It's not a thermal distribution function, but there is an attempt towards thermalization. So what happens is that lower momentum modes start getting filled up through these collisions. The thermal distribution is this black one. Now, the important effect of these collisions is that because the lower momentum modes are getting populated, the average dark matter velocity at late epochs gets reduced. So if you do not include these scattering effects, for example, the free streaming length that I mentioned will be around 73 kiloparsec, which will be already in tension with the Lyman alpha data for this scenario. But once you include the collisions, there's a 40 times reduction in the free streaming length, thereby making it allowed. So even in such a simple scenario, there are many details of the inflationary and the reheating epoch that are important. And that brings me to point out this first set of unknowns that one might have a discussion on. So as we saw, the dark matter distribution function crucially depends on the reheating phase, but we do not have any good observational probe of the era of reheating so far. Of course, if primordial gravitational waves, they must be generated during inflation. If they are discovered, as Tanmay was also discussing, then the Hubble scale at the inflation will be known. So that will be one less parameter unknown. But still, the reheating era is unprobed. So for example, the duration of the reheating that I mentioned, things like that, or the equation of state during reheating will be unknown. One suggestion to probe the reheating era might be to study the evolution of the gravitational wave amplitude, because those will be sensitive to the equation of state parameter during the reheating. If you look at the evolution equation for the gravitational wave amplitude, these are the Fourier mode evolutions, they depend on the scale factor and the derivative of the scale factor, and those will be sensitive to the equation of state parameter during reheating. So maybe studying the spectral shift of primordial gravitational waves can give us some information about the reheating era. So that is something that we might discuss. Okay, so let me move on to the second and last topic that I want to mention, which is the gravitational production of dark matter. So an expanding universe can lead to particle production. You can think about analogies. So in quantum mechanics, you may think about a simple harmonic oscillator with a time-dependent frequency, or even the undergraduate problem that we all solved. There is a particle in a box, and the size of the box is suddenly doubled, and then there is a probability now to find the particles in the excited state of the new box. So that is the analogy. To be a little more technical, since the metric in an expanding universe is now time dependent, the equation of motion of the massive fields will differ from the Klein-Gordon equation in Minkowski spacetime, and therefore the Hamiltonian and the instantaneous vacua are also time dependent. And now if you think in terms of Heisenberg picture, even if we start out with the vacuum state of the field at early times, at late times that state will have a finite density of particles, just by this simple analogy. And this contribution, again I would like to emphasize, is always present. The exact density produced may depend on the Hubble scale at the end of inflation or the reheat temperature, but this is an irreducible contribution. Just to flash some technical details of how this computation is performed, these things are being studied since ages. Schrödinger wrote the first paper on this, and there are seminal works by Parker, Zeldovich, Starowinsky, and so on. You might look at this recent review by Kolb and Long summarizing these things. So we have this time-dependent metric, and you can start with the action of a scalar field coupled to gravity in this metric. Now the kinetic term is not canonical because of the presence of this minus root g and d4x. So to make it canonical, you make this transformation with the scale factor. Now this rescaled canonical term is now, kinetic term is now canonical, but you end up with the time-dependent mass for this scalar field. So that is the key quantity. And therefore the Hamiltonian is also time-dependent, as I mentioned. You can obtain the equations of motion. They differ from the Klein-Gordon equation because this mass term a square m square effective is now time-dependent. You can do a mode expansion. The space part remains the same because space translation is still a symmetry, but time translation is not. So the time part is now a new function. And the mode equations are equations for harmonic oscillators, but with this time-dependent frequency that I mentioned. Okay, and that essentially leads to particle production because the vacuum state at early times is not the vacuum at late times, and therefore contains non-zero energy density. Now, with this second scenario in mind, there are some possible theoretical directions. So the first scenario, there are some possible observational directions, and for this there are some possible theoretical directions that one might discuss. The first is improving the computations for spacetimes that are asymptotically FRW and not Minkowski. So most of these computations are easily done if the asymptotic spacetime is Minkowski, where you can define particle number properly. But we are living in spacetimes which are asymptotically FRW and not Minkowski. There are some approximation schemes that are usually used, but one might be able to improve these computations. The second thing is what if interactions are present. For example, if we started with a scalar field, there may be cubic or quartic self-interactions of a scalar field. And in the presence of interactions, these equations are no longer free field equations. They are modified, and so the mode expansion becomes much more difficult. And in this case, what happens? So that is another interesting thing to think about. Once this is known, one can compare between different production mechanisms. For example, between the gravitational production mechanism and other production mechanisms induced by different couplings. So these are the two things I thought I would point out for possible discussions. And now we'll move on to Debtosh. And probably we'll take questions in the end together. Okay. Thank you. I mean, we thought so, yeah.
So first of all, I would like to thank the organizers for this kind invitation. So as Chowdhury had already said, that organizers asked us to summarize the dark matter in cosmology into three parts, where Chowdhury started with the early era, and what I plan to do is what will happen is in the intermediate era, and I'll explain what does it mean. So basically, so this we know a couple of things. So the earliest thing we know that, as Shothoda has pointed out, that the BBN is around 1 MeV or so. So for a successful BBN, the temperature should be around a MeV or so. And as Tanmoy and also Shothoda said, that there is a need for cosmic inflation. So now cosmic inflation is there and BBN, but in this middle part, this green shaded area, is basically we do not know anything about. All we know that the universe must be in a radiation dominated by the time BBN sets in, basically. Okay, so that's 1 MeV, say. Now the point is that the question at this era, this green shaded area, comes like what kind of physics it gives us. For example, as we know that the need of the dark matter, so dark matter can also get produced from in this era, as well as this could. So the point is that if the dark matter gets produced, how do we know? So one thing we know about dark matter, apart from the gravitational interaction, is the radic density. So the set of works which actually encompasses like this era is basically the production of dark matter. That may be gravitational, that may be some via some mediators, and that basically leads to a set of plethora of papers which has been generated since last 20 years, that different portals which will generate dark matter, which is basically DM genesis in the very early universe. So it could be a portal of a spin 2 graviton, it could be a spin 1 dark gauge boson, spin half some fermions or some scalars also. So there are basically there are soup of standard model plasma, and from there the dark matter gets produced. So this is one of this like a very basic picture. So where, as you can see, that at the end of the inflation, which is somewhere here, so the inflaton is, this is inflaton energy density in some scale, in some units, and then as around the time when the inflaton decays, because it has to decay so that the universe enters in a radiation dominated era, so that inflaton density decays and the radiation density increases. And as you can see, this period onwards, so around 10 to the power 3 and above, the universe is a radiation dominated era. Now at the same time, if there are some like relic dark matter particle, depending on various parameters, maybe the mass, the in this case a scalar mediator, so that dark matter can also get produced via the 2-to-2 interaction to the dark matter. So like the radiation which is being generated from the decay of inflaton, that actually on the way also produces dark matter. So this is a very basic picture of dark matter production, and in this case, in this particular case, it was basically a freezing type of dark matter. Now the point being that if the most of the intermediate stages of dark matter production is basically through this. So there are some changes into this production, whether this dark matter, whether the radiation which gets generated from the inflaton decay, whether they come into direct thermal contact or not, whether they thermalize or not, then there are a lot of other effects one can attribute to this dark matter relic density. Okay. Now the point, one thing is quite interesting is that there might be, as we say, like inflaton is a matter content and matter particle, but there might be some other also matter domination. So universe might have gone to various stages of matter domination prior to BBN, prior to that. And as you can see that for any metastable field like phi, the energy densities would actually, ratio of the energy density would just go as with scale factor. So at some point of time, even if this phi was there at low values, but the ratio will increase at some point of time, the phi will dominate. But then phi cannot be dominated as throughout the space, because by the BBN the phi has to decay, universe has to go to the radiation. Fine. Now the point is there are a lot of BSM candidates. There are a lot of, again in this area, a lot of papers which talks about the dilaton or a moduli or a curvaton kind of scenario, where this which is basically the metastable field, via which the decay of which would actually generate the reheating, or the universe enters the reheating phase. Now the main constraint as all of these classes of model is that all of this, the metastable field has to decay by 1 MeV, okay, by 1 second. Now the decay proceeds via dissipation rate of this metastable field. Now the metastable field at this very high temperature, so there is of course the non-negligible finite temperature corrections to this metastable field, and which finitely also affects this dark matter, say, production. So one can directly see that if, for example, that oscillating scalar field has a potential phi to the power p, so then if it only couples to the fermions, the decay width or the dissipation rate goes as mass of the scalar field, which actually scales as a to the power minus the power of this. Or if it is a bosonic decay, the scaling is just opposite of each other. Okay, and as you see that the mass also has a field dependent quantity because it's second derivative of the potential. So via this phi one gets this A changes or the dissipation rate. So dissipation rate is never a constant at the very early universe. For example, in a more like model dependent way, you can calculate that the moduli actually decay goes as TQ. Now, so rather than going into a particular model, so that means if you have a particular model, go into that, calculate this and do that. One can also take a separate path that parameterize the decay width in terms of T and A, okay, and those powers, and depending on the powers of those and the equation of state of the phi of the scalar field, one actually could show that during such early matter dominated era, due to the decay, the temperature not only increases over scale factor but sometimes also decreases. As you can see, and in this case, that when this power is 1 and the others are 0, that universe during this the dissipation of the metastable field, the temperature decreases. But there are some other cases where there are increasing of temperature. In this peculiar case, where this it goes as the dissipation rate goes as T to the power cube by phi square. Now, basically what happens, so the temperature decreases or increases, one thing very common is that entropy gets injected. Basically, this phi gets decays pushes a lot of photons into the bath, and as a whole, as you can see, for different colors, so different colors basically corresponds to different of these n, k, omega values. As you can see, there is always an increase. So this is the entropy produced, so there is an increase of that. And now, if you just calculate, put that back into the relic picture or into the yield of the dark matter via the production, as you can see, different this n, k, omega values gives you different final relic density. Okay, so basically, if you start with some relic density, but due to the decay of the metastable field, it pushes in entropy, and as a result, your final yield would change. Okay. So now here, what we actually use that as a probe, that as we know that freezing type of dark matter generally features a very small coupling, because in case of freezing, the dark matter and the standard model particle are never in thermal contact. But one could achieve, like in a case study of a dark photon portal scenario, one could achieve such coupling could be as large as in the presence of an EMD, which is comparable to other experiments. For example, in this case, there is a constraint from supernova, there are some beam dump experiments, and on these colored lines again correspond to different n, k, omega values. These colored lines, the relic is satisfied. Now these are on these lines, the relic is satisfied, whereas as you can see, for a purely radiation dominated universe, the coupling would be as small as 10 to the power minus 10 or below. Okay, so that means if universe, just we do not know that universe whether it had any early matter dominated era or not, but if it is the case, then there is no hope for detecting this kind of epsilons. Okay, whereas if we are lucky that a freezing type of dark matter, as well as giving some as well as answering the dark matter puzzle, can be probed at the experiments, the low energy experiments. So this is one of the case which basically tells you that in this intermediate matter dominated phase, the effect of it on the dark matter physics. Okay, so where finite temperature corrections are important. Now the question is that, so this kind of plot basically tells what, that there is a relic density satisfied, okay, and also there are regions of the parameter space are in the radar of experiments. But what are the really true signatures, because you see that we just see some relic density, but what are the really true signatures of such an EMD? To do this, so one thing one needs to understand that how dark matter decouples. Now, as you see that in this onwards, I will talk about a dark matter which is non-relativistic and it's a produced via freeze out of mechanism. That means that the dark matter and standard model, the the equilibrium is no longer true below the temperature T freeze out. Now, at this temperature, only the dark matter can annihilate into standard model, but not the other way. So, in the standard radiation dominated epoch, the dark matter first decouples here. That means I have only one channel, one unidirectional channel, that the dark matter particle can go to the bath particle. Below that temperature also, that since dark matter particle is still in the bath and the standard model particle is also there, so they can kinetically couple with each other. That means standard model dark matter can still go to standard model dark matter. But again, as the temperature goes down further to some T kinetic decoupling regime, so only one of this channel also stops. So that means below TKDS there are no dark matter and standard model particle in contact, and we call that the dark matter completely decouples from the plasma. So this was not the only phase of TFO that the dark matter was decoupling, but TKDS is actually decoupling of dark matter from the plasma. And if in a simple picture where the interaction governing the freeze out also governs the kinetic decoupling, one can directly show, this is the back of the envelope, that the freeze out always precedes the kinetic decoupling. So always first freeze out, then kinetic decoupling. Now this is in a standard radiation picture. Now what will happen that if there is a intermediate matter domination during this time? So what happens, the dark matter thermal decoupling in an early matter dominated era. Now if in the early matter dominated era, the conditions still remain the same. The first one is to check whether whether the dark matter standard model annihilation rate is equal to the Hubble or not. Then one is to check whether they are kinetically coupled or not. But there is one thing is quite crucial in this case, is that the Hubble rate is changing, because in intermediate matter would change the Hubble rate, as well as the elastic scattering, how it changes over temperature. So having an intermediate matter domination, as we saw, the temperature can increase or decrease. So that means the temperature variation in an intermediate matter dominated era has non-trivial values compared to the radiation dominated. Radiation dominated Hubble is always going as T square, right? So now in that case, if we go that when reheating starts, so that means when this metastable field decays, when its dissipation rate is higher than the Hubble. Now for a constant dissipation rate, the T goes as T to the power A to the power minus 3 by 8 and Hubble goes as T to the power 4. So this is different in the case of radiation. Radiation it was T square. Now so first at some temperature one achieves the chemical decoupling. Below that, one needs to now assume that what is the channel via which the standard model, the elastic scattering proceeds. If the elastic scattering proceeds via an S wave, so that means the sigma V elastic is constant, then the elastic scattering, the momentum transfer in the elastic scattering and the Hubble, they both scales at T to the power 4. So this means the dark matter, so this process is always there till as long as the metastable field is there, right? Because both scalings are the same. So that means if and only if this elastic scattering was faster than T to the power 4, then only it is possible. And for an S wave, this is not possible. So that means for a constant decay, the upshot is that for a constant dissipation rate, even in AMD, for an S wave channel, it is not possible to decouple fully a standard dark matter from the bath. Now, what has been shown already, that if the elastic scattering is via P wave, then the gamma elastic is T to the power 6, but the Hubble is T to the power 4, so that means it is falling faster. So that means in the case of P wave scattering, one can decouple, and the dark matter decouples in the matter dominated era before the onset of reheating. So this was actually dubbed something called partial decoupling of the dark matter. Okay. Now, so this here I try to show that, as I said, that the dissipation rate is actually a temperature dependent quantity. Now for a very simpler case, when the dissipation rate is only dependent on temperature, the T and H scalings are different. So in that case, one can actually show you, I'll give you some explicit examples, that the S wave is itself enough to get it decoupled in the matter dominated era. So one need not go to the P wave for this decoupling of the dark matter in the matter dominated era. And now since the dark matter is decoupled in the matter dominated era, so then this free streaming length is larger, and in that case also the dark matter power spectrum also receives large boost from the matter perturbation during the EMD. So as a result, there will be some structures, more structures forming in the early matter dominated era as compared to the radiation era. So this one can actually go via, like in a short way, that usually the temperature is defined like this from the distribution function, and they follow an equation. This is the dark matter temperature T chi, and T being the temperature of the bath. So now you can see that when these two terms, these and that terms are very small, the temperature of the dark matter falls as e to the power minus 2, whether we know that temperature of the bath falls as e to the power minus 1. So that means the temperature of the dark matter falls faster and they decouple. This is a standard radiation dominated picture. Now the point is, in the case of non-standard scenario, the Hubble changes with temperature as well as the temperature change with scale factor are different. So one can actually if you just write and this elastic scattering, if you write like parameters like this, where n, small n being 0 is S wave, n equals to 2 is like P wave, and so on. So then one can actually write in an approximation the dark matter temperature looking like that. So that means when this term or the exponent of this term is lesser than 2, so then larger than 2, then what will happen? This term will fall faster, then this term will dominate than that. So that would actually lead to main two different key things, that whether the dark matter fully kinetically decouples in the matter dominated era, or partially decouples, or no decoupling at all. Now one can directly show that even for a matter, the equation of state of 0, the dissipation rate, if I parameters like this, when I take the dissipation rate being temperature dependent, already the S wave shows a partial decoupling in the matter era, whereas a P wave shows a full decoupling in the matter era for T to the power for the exponents of K as 0, so like no A dependence but T dependence being 1. Okay, so this was one can achieve. So this was not this was something which we have shown, that the non-negligible temperature dependent correction due to the finite temperature corrections, one can achieve a full decoupling in the S wave with the S wave elastic scattering also. So this actually also we have shown in this panel. So where these different colored band are nothing but the free streaming length in the matter era versus radiation era, and as you see, only we had plotted the ratio of where these bands are less than 1. So that means there are in the free streaming length is always smaller as compared to the radiation era. Sorry, this is the opposite. It is basically the AMD by radiation, and this on this different contours actually show the elastic scattering. So elastic scattering being 1 and less means there is the unique vertex which gives rise to the relic density as well as elastic scattering, and in most of the parameter space, where the relic and the elastic scattering comes from the same origin, that means these contours has to be less than 1, one actually sees the ratio being small. So that means the EMD, in the EMD era, the free streaming length are different, lesser than 1 as compared to radiation. So radiation era has a larger free streaming. Okay. So now this also one can see in the power spectrum data. So in the power spectrum, so here we compared with against a power spectrum of a dark matter which decouples in the radiation. So it's basically it's very large as compared to a simple like a fermionic model or a dark matter or a scalar model being model 1 and model 2. So there, as you can see, that one can see that in the power spectrum, little larger value, there is some boost in the power spectrum as compared to the radiation era, okay, and the standard radiation picture, okay. And this basically comes from in these two simple models. As you can see that the free streaming lengths are different, not equals to 0, okay. And this actually finally takes us to a plane of, for example, in a S-wave scattering for a scalar dark matter, in the scattering coupling versus mass, a parameter space one can find out where there will be more structures in the dark matter halos as compared to the standard radiation picture. So anything below this straight line and in that colored region have more structures in the dark matter halos as compared to the radiation picture, in the standard radiation picture, and above this there are no additional structures. Similarly, in the case of fermionic dark matter, also one can delineate the parameter space where there will be more structure versus less structures, okay. And I just flash the elastic scattering in these two cases. So this basically takes me to the final question that, as I said, that if there is an EMD era, so I should see more structures, and those more structures will be a probe. So a probe of those more structure could be somewhere where there are more and more dark matter halos, maybe dark matter annihilation at the galactic centers, or also when you have galaxy surveys, one can try to see that what kind of masses I see compared to the standard radiation picture. So for here, I was showing this halo mass fraction as compared to the standard picture. So as you see, in the standard model 1, the mass fraction is around the subsolar mass, and these two different. So this final at z equals to 10, if you see for the scalar dark matter versus the fermionic dark matter, the mass fractions are different, but they are all sub-Earth mass halos. These are as compared to, in the case of pure radiation, I don't see any of such. So one way to see such scenarios which satisfies dark matter but also gives extra halos of sizes in the sub-Earth. So that is one of the way to see if an EMD era was existed before. So that is one thing which I felt could be interesting to understand. If there is an EMD, what are the signatures of such an EMD? So this is one of the signatures, and then another thing which I was thinking is that, I mean, so far as we all talk about that there is a reheating and the lowest bound of reheating is a BBN. So is there any particular way we can think of that how to constrain reheating temperature? Because so far reheating is just a free parameter in this entire business. We set the lowest value to be, say, 10 MeV or so, few MeVs. So how do we know? So what could be the other probes of such an early matter dominated era before the onset of reheating universe? So that's the two questions which I would think. One of the thing I think could be this kind of structures. One could go, it will show up in the structures in the parameters. These are very simple models just to show that there are additional structures in the EMD as compared to the radiation. So maybe at a later survey of LSS could try to see at different galaxies if they go, and they can see what's the typical sizes of halo you can see. So that could be one of the things. Okay. So this then I'll stop here and maybe I'll go to the give it to the speak. Thank you.
Okay. Yeah. So it was decided that the mandate of my talk is to discuss the implications for structure formation on dark matter, not because I know much about this, but I was found equivalently misfit for all the epochs. So by natural justice, I got the last slot. Okay, so here is the power spectrum. Now we know that for sizes more than the size of galaxies, we have very good data from galaxy surveys and CMB. And therefore, for all kind of dark matter models, we are kind of confined to cold dark matter. And so we have very little wiggle room here So all the fun with model building or dark matter and everything is to have a non-trivial modification at small scales, where we have some still, because if you go to length scales below 1 megaparsec, the resolution of observation goes down, and therefore you have some possibilities to do non-trivial things there. So this is the scale where you can think of situations beyond cold dark matter. For example, warm dark matter, fuzzy dark matter, and all these things can produce some deviations of the power spectrum in this regime, and you can still survive most of the observations. So here is like the model space of various theoretical model, and if you look at this plot, okay, maybe this one for theorist is better because this is like the coupling versus the halo mass function, and this is better for the astrophysicist, and this is like the line of linearity versus non-linearity in the collapse. So anything above this is purely safe. So here is like SUSY dark matter models, which are basically cold dark matter, and everything is safe over here. But then you have a few dark matter models which brings you into the nonlinear regime, where you can create this non-trivial constraints on this small scale structures. So where you can have some deviations, and then you can look up into the structure formation observations and data and see whether your models are inconsistent or inconsistent with them. So one of the main issues in small scale which survives, or let's say at least at some level survives, is the core cusp issue, because the missing satellite or too big to fail problem sometimes depends on how good your n-body simulation incorporates things like baryonic physics and others. So they are more dependent on who you are speaking to. But there is somewhat of an evidence of this core cusp problem, which is related to the issue that if you look at the interior of galaxies larger than dwarf galaxies, so if you look at mid-sized galaxies or clusters of galaxies, towards the center, you would, if you have a collisionless dark matter, you would have expected them to just coalesce into a cusp-like feature. But in many of them, you see a code behavior, which is what you are seeing here in this observed rotation curve, where you see that the rotation velocity follow a behavior. These are the observed rotation curve, which kind of follows a more code density profile than an NFW profile, which is a cusp profile. So there are many observations, but there's also a variation of this code, which is also a kind of an unresolved problem. And there are many solutions to this thing. One of them is, of course, the fuzzy dark matter solution, which is an exotic solution for core formation, where you assume that at the center there are these solitons which are formed, which is the region where dark matter has coalesced to a situation where the de Broglie wavelength is greater than the inter-particle spaces, and then far away in the in the periphery of the halo, they are still behaving like very rare classical dark matter, because the de Broglie wavelength is probably smaller than average interparticle space. So there's one possibility. The other possibility, which I would explore a bit more with a few more slides, is the self-interacting dark matter. So the idea here is that, the reason for this core formation is that there is gravitational cooling. So basically, as gravity collapses, it basically, cools down the interior of the galaxies, freezing down all kind of motion, gravitationally freezing them down, and it cools the interior further, and that kind of accelerates the core, the cusp formation for non-collisionless cold dark matter. But if you add in some kind of self-interaction, the self-interaction allows us a channel to transport heat from the periphery of the halo to the central region, and through this you can thermalize some amount of the interior region, and this thermalization, this transport of heat from the periphery to the center creates pressure. The central region being thermalized, it can recreate a pressure which can kind of resist some of the gravitational collapse, creating a core-like structure there. So this is how you can create a kind of a core through self-interacting dark matter through thermalization, and one can have a very quick estimate of what that size of a core would be through thermalization using this expression over here. So the idea is very simple, that as you move to the periphery from the interior, the density falls down. So you can estimate that the size of the core would be that distance from the center of a galaxy where the density has fallen off to an extent that would still would be able to sustain at least one self-interaction in the lifetime of a galaxy, let's say. So this is basically that, in the age of a galaxy, the number density is so that it can at least have one interaction in its lifetime. So that would kind of tell us what is the core radius, okay? And this would typically be the size of that core. And one can actually go ahead and incorporate and figure out what this core radius would be in real n-body simulations. So a couple of years back, we tried to do that. We kind of did some isolated halo simulations, around 50 n-body simulations of isolated halos, where we kind of the halos ranged from low surface brightness galaxies to clusters of galaxies, and we also ranged the self-interaction from 0 to I think 10 centimeters square per gram, and we tried to see these core formations, and we extracted the core radiuses from these isolated halo simulations, and we compared them with the observed data in galaxy surveys, and then you can put some very conservative limits on the self-interaction of dark matter. For example, we got around 9 centimeters square per gram, which is conservative in terms of the limits already that exist from bullet cluster. But remember, this analysis that we did a couple of years back, we did an averaging over all kinds of galaxies, from low surface brightness galaxy to clusters of galaxies, and some of them actually do not show a core. Okay, there's a variation in cores. So we tried to do an averaging over all kind of galaxies, and also this was a dark matter only simulation. So if you add baryonic effect and things like that, that would add more core formation, because baryon also helps aiding this thermalization of the interior part of the core. So it increases core effect. So if you do not average over many different galaxies and focus on, let's say, large galaxies or where core actually exists, you will get a better limit. And if you incorporate baryonic effect, you will get a better limit. So this is an updated result done by Odhikari et al. Published this year, where they look at a similar kind of an, of course, a much more detailed n-body simulation and over a cluster galaxy, and they compare it with microlensing data, and they get a limit which is even better than the limit that you get from bullet cluster, and it's just 1 centimeter square per gram at 90% confidence level. You can also get limits from on these kind of dark matter models. Okay, let me just keep this for lack of time. Let me just keep with SIDM for now. The other kind of things that you can also think about, this is the effect of self-interacting dark matter on the distribution of matter in galaxies. The other distortion that you can expect from self-interaction in structure formation is its velocity distribution. So if you have self-interaction, the velocity distributions function will also be distorted because of self-interaction. So and why we would be interested in them very quickly, they feed into all our detection sensitivities. For example, all the the limit plots that we flash for direct detection, indirect detection, or whatever, they all depend on what kind of velocity distribution function that we are feeding into them, which are usually taken to be Maxwell-Boltzmannian. But if you consider this kind of SIDM paradigm, they will all distort these velocity distribution function, and these things will have large error. So since we had all this simulation lying around, we tried to fit in a generalized function and check what kind of distribution distortion we would get by just simply assuming some kind of a random polynomial or whatever you can get into this data. And statistically we did some analysis now by segregating galaxies which are of Milky Way size, low surface brightness size separately, because otherwise the statistics gets messed up. And we took a very rough ansatz, and this is like the statistical fit, and we tried to compare it with the measurement, for example, we know from the solar rotation curve, and from that also you can give some limit on the self-interaction, and it so happens that this data gives a slightly better fit around 2 or whatever. But this is just an exercise, but what it shows that this self-interaction has 2 kind of impact on structure formation. It changes the distribution, it also changes the velocity distribution. So I think that's all. So I think the main issue is that everything about dark matter that can affect structure formation, the main principle is that it has to only affect at small scale. And the main, I think the hottest candidates are warm dark matter, fuzzy dark matter, or self-interacting dark matter. And I think the right way to do the limits from structure formation is to do n-body simulation for these things and try to study about them. But the problem with n-body simulation is that you have to, every time you have a model, you have to implement each interaction separately and run them, and it's very computationally heavy. So this is basically what I wanted to say. So I think we should conclude, and Shotto, maybe we can we can just take questions in general for all the parts. Yeah. So Shotto, you want to conduct this general? If there are any questions, we are happy to take about the entire part. Yeah. Yeah, there's a question here.
Hi, I have one question regarding Debtosh's talk.
Yeah.
So this is regarding, I mean, you said there will be a structure enhancement on the high K values, and you said we can see them in like galaxy surveys. But I mean, these are very small length scale, and I don't think they will form. I mean, galaxy by galaxy, I mean, they will not form stars in them. They will be just dark matter halos. So are you saying they will be seen in galaxy surveys or by lensing or some other observation?
Yeah, sorry. I mean, I should have been more clear. So these are anyway sub-Earth size, so they are not bigger. So all I'm saying that there could be some smoking gun signatures where there are more dark matters, but as of now, I don't have much in mind. Whether not in the LSS right away we will see, but where there are number density of dark matter are large, so there we might see some annihilation signatures. So we are thinking of currently what could be a possible ways to see.
I think lensing can be one of the things.
Be.
Annihilation is of course there. I mean, if you see some signal from
directly coming down to this low scale, I'm sure it's not LSS. Probably would not. Yeah, this is sub-Earth method.
Okay.
Sub-Earth.
Okay.
Yes.
Thanks.
Yeah.
As Sabatma halos detectable by lensing?
This I also do not know. This is so Sabatma's halos are detectable by lensing, is it?
In principle, yes.
Okay.
For that, yeah. Microlensing can do it.
Okay.
Also, I mean,
Depends on the size, to be honest.
So what is the limit on the size that is accessible to microlensing?
Like minus 17 or so. But right now you can probe till 10 to the power minus 14 solar mass.
Solar mass. So this is even smaller compared to the ratio. So we are.
That's a point.
Okay.
Sorry? That's points.
Ours are like
Oh, right,
extended, right?
Yeah. Yeah, it will slightly get degraded. You will still can do better with forthcoming X-ray telescopes like Strobe-X.
Okay. Yeah, I mean, I'll be interested to actually look into that. Yeah. Nirmal, you were saying something? Yeah.
Should I? Okay. I must say, first of all, that I very much enjoyed this sequential presentation by the three of you, which was so well thought out and logically connected that it was quite enlightening. But I am asking this question to address my own lack of understanding a little bit. For example, Debtosh's treatment of the era around nucleosynthesis and Tirtha's treatment of the large-scale structure formation made use of some model effect, some portal effect, some self-interaction strength, or things like that, in order to address the various observables related to these two eras. What I want to understand is, in the backdrop, or I should say in the foreground, with these effects that you talked about in the foreground, the background, or rather the backdrop that Chowdhury tried to outline, one of the features, namely the production of dark matter through geometric effects in the very early era, which is a very interesting effect, whether the effects of that can still kind of have its signature left in the observations which are model dependent, as discussed by the two of you. In the background of this, can Chowdhury's geometric effects still show up in something that is observable?
Okay, so there can be isocurvature perturbations. Okay, so-called. The standard CMB feeds tell us that the perturbations in different energy densities is adiabatic. So they are proportional, right? Perturbation in proton density to dark matter density to photon density, they are all proportional. Okay, so that's adiabatic, and that fits the data very well. Okay, but if the dark matter production is completely unrelated to the production of baryons and photons, which is what this gravitational production is, then there can in principle be isocurvature perturbations, which is a difference from the adiabatic ones. Now, whether...
So it will be a combination of the two, because the adiabatic perturbations are bound to be there because of interactions. On top of that, you are talking about the isocurvature.
Yeah, so suppose there are no interactions, and then it's isocurvature, right? It's different from the perturbations in protons and photons. Now, whether that is allowed or not is a detailed question. So, one often finds that you might get a power spectrum which is proportional to kq. K is this wave number, and so that will lead to isocurvature perturbations at small scales, which are not constrained by CMB observations so far. But maybe in future, right, you see some isocurvature perturbation, so that will be a signal definitely.
So there will be distinct signals.
Yeah. And if your model produces... Yeah, of course. That's what I'm saying. So CMB highly restricts isochromatic
Yes,
perturbation.
I would think so. That's why I was
But
thinking.
suppose the power spectrum is proportional to some nth power of k, right? Then only the isocurvature perturbations will show up mostly in small scales. And that CMB doesn't constrain yet. Yeah, but not as strong as in large scales, of course, right? So if the power spectrum that is produced, for example, is logarithmic in k, then those scenarios are completely ruled out. Okay.
Once you are showing this particle production, so there is this you have taken the flat FRW matrix on kind of flat part.
The spatial sections are
Spatial
taken to be
flats,
flat
but you have
based on the
part of
current CMB data.
Right. So you have part of FRW matrix, right? So you have matrix scalar perturbation already there, which you need to couple. Otherwise, it is not gauge invariant. So there is a small,
So
large.
only the background part was considered, right?
So the perturbation part. So you are considering particle production, which is the perturbation, right?
Right. But the only important thing for that part is the time dependence of the metric. Okay.
Yeah. So there is so that's time dependence of the metric. But if you are considering perturbation,
Yeah.
there is scalar perturbation coming from the metric as well. You can have
Those metric fluctuations won't be that important because
No.
they are 1 in 10 to minus
Those
5.
their scalar part would be important because they will couple together with the scalar perturbation that you are talking about. Unless it
Yeah.
will not be gauge invariant.
If they mix, of course, then one has to be careful.
There has to mix, right? Because it's a scalar perturbation and you have a scalar perturbation
Sure. So
from
if
the
they
field.
mix, then one has to be careful, right?
So-
But they might not mix also. For example, if your dark matter is,
On certain
stabilized
gauge-
by some Z2 symmetry,
On certain gauges, they don't mix.
then
So
it may not mix with the inflaton, right? So the inflaton may have a different Z2 charge than the dark matter, and then they won't.
No.
mix.
I don't think that has anything to do with Z2 charge of this thing. If you have scalar perturbation coming from some scalar field, and you have scalar perturbations coming from FRW metric, scalar tensor decomposition,
Yeah,
you have to construct a gauge invariant perturbation.
that is true. But for that, you need a coupling of the scalar with the dark matter. Like you need
You
a
have square root of determinant G.
no. But you need a coupling. Otherwise, how will they mix?
Yeah, please.
If we can pull up. Can you pull up? Yeah. So if they mix, of course, but yeah, they may not mix necessarily because they may be protected by symmetry.
So this one here, what he says is right. Can you go back to that table?
Yeah.
So you see the Ricci part. So basically, with the perturbation, you can add a phi on the diagonals and do the whole computation. Once you rescale the field with A inverse, the Hubble parts cancel from the Hubble part coming from the Ricci scalar. But the second derivative term on the scalar perturbation remain. That contribute to the Ricci scalar. So in principle, once you assume a power spectrum for the scalar perturbations, coming from the scalar perturbation, you have to plug it in and then solve these equations. So this effectively means in your mode equations, you'll have a source term on the right hand side.
Yeah. That depends on the value of xi, of course. So
Yeah. So if you assume just an inflationary power spectrum like which is only tested at the first few E foldings, this will have a non-zero contribution, but it's not significant.
Right.
But if you have a KQ thing, KQ power spectrum, the IR power spectrum, in principle you can have large contribution.
Sorry. So yeah.
Can you throw the laser pointer on this?
Yeah. So this term you mean?
Yeah, there's a term coming regardless whether there is coupled with the thing. Once you assume that the G is a
Okay. Yeah, but I still think that the dominant time dependence comes from this background metric time dependence, right? Not from the fluctuations.
So
Sure.
you're doing this, that is eta mu nu plus you'll have a delta eta mu nu.
Yeah.
So the delta eta mu nu will contribute to this. That's his point.
Yeah. Okay.
Because at small scales you have the very poor constraints on the power spectrum, it is allowed to play this game.
It will blow up your production because it has a tachyonic part.
Okay. I mean, by all means, I mean, okay. I mean, if it blows up, then of course you will get more. Usually what happens in these scenarios is you get less. Okay, that's the problem because it's gravitational production.
Okay, let me.
Of course, there are some technical details. In certain cases, you can get more, but usually you get less. And if you get more, that's okay, I think.
if you get lets, does it get submerged in the subsequent effects?
That depends whether it has other couplings or not, right? So that was the whole point. If it only has gravitational couplings, then this is the leading production mechanism.
Wait. So for simplicity, assume everything is Weyl invariant. So your xi there is 1/6, and the mass term, the eta dependence goes away. But even in that limit, you'll get a contribution from the Ricci scalar in the upper part of the Lagrangian, which has derivatives of the scalar potential.
Yeah, still. I mean, even in that limit, there is a time dependence, right? Because there's a square sitting here.
Yeah, no. So you do the rescaling there, right? A inverse that removes the a square dependence.
In terms of this rescaled field only.
Fine. Do massless. That doesn't matter.
Of course, massless fields cannot be produced in this way, right?
But with scalar perturbations, you can. That's his point.
Sure, that's your gravitational waves and so on, right? You can produce.
The production of that particle, production of the chi that is that particle will be produced.
So because you get a source term on the mode equation on the right side.
Yeah, so the claim is that you can produce massless particles by this method if you include perturbation. Is that the claim?
That's the claim.
Okay. I have not seen this in the literature.
You will see it in 2 weeks.
Okay, so maybe we'll just wait for that. So that's that.
Also in the market as well.
Okay, so that's good. Yeah.
I have one question.
Yeah.
Is there any minimal value? No. Can you get a minimal value for the self-interaction coupling?
Yeah.
Or comparing the data with the simulations?
Yes, I showed them. So we got around 9 centimeters. Yes.
9 by something. Like
Yes.
But that's still large, right?
That's still large. Bullet cluster gets around 2. So the bullet cluster limit is around 2. But there are some other groups that I showed, like Orko Banerjee from IISER Pune. They have done a much better simulation and a much better comparison. So they have like 1 centimeter square per gram at 90% confidence level, which is better than bullet cluster. And from the velocity distortions, we also compared, which we are still working on. From that, we are getting around 2. But ours are very crude, dark matter only n-body simulations. And the state of the art is with some
Sorry, can I say something? So,
Yeah.
So technically, what you are doing and what Orko and Suspita are doing are different because you have different mass scales.
That's true.
So if you have a velocity dependent thing, then you can say that they are at 1 because they are clusters. So effectively, they are using basically bullet cluster, but they are not using bullet cluster, but that's why they are stuck at that number 1.
That's right.
Whereas you are using a different mass scale, so that's why you are slightly.
Yeah, I'm averaging over many mass scales.
Yes.
That's also a problem.
But do you have clusters in that?
Yes.
Yeah, but it depends on how many you have, right? Then because if the weight.
Yeah,
the
weightage
cluster-
is there. So we are having around 3 clusters in
But and how many Milky Way like galaxies you have?
4 or something like that.
And the low surface brightness?
3.
Okay, so that pushes up.
Yeah, that is what is basically pulling us down. But then, if you want to model, my point was that if you want to model an uniform self-interaction, you have to have it for all.
No, I completely agree. I'm just saying that's it's not a one-to-one correspondence.
Yeah, I agree.
I agree with what you're saying.
Okay.
Yeah, thanks.
Okay, let's thank all the speakers.